Hello everyone. So for this primer video segment today, we're going to be talking about memory in C. And this can be a difficult subject, but it can also be the key to a lot of uh, important ideas in programming, especially low-level programming. So first thing I wanted to do is review this. This is our little diagram of how memory works in a C program. This will be pretty much any C program, though. Depending on your system, it could be things like the data segment could be up here or something like that. But it's going to roughly follow this pattern. So for right now, let's look at these. We have text. The text segment is this is going to be where your code is actually stored, where the machine code running to run the program is. This is also going to sometimes contain like um, certain constant data, especially string literals. That'll actually be stored in the text of the code because it's constant and it's often more efficient to store there. Um, so we have text. Initialize data. This is going to be mostly your these two segments tend to be lumped together as just the data segment. I split them up, but initialized data is going to be your global variables that are already have a value, and uninitialized data, or the BSS, is going to be global variables that don't have a value yet, that are uninitialized. And this is the same for static variables as well. Um, then we have the heap. This is going to be a upward growing segment. This area, by the way, is just garbage memory, which is why we want it to stay that way because we don't want the stack and the heap to collide. That can happen. Usually doesn't happen though, because this area is quite large in the middle there. Um, Virtual memory, so it's large address space. Um, so the heap is going to usually be our dynamically allocated memory. This is, well, things that we get from malloc or calloc, or if we're using C++, this is going to be things we get from new. Um, Regardless, this heap memory is going to have certain properties that the stack doesn't, but it's another source of memory for us. Stack, on the other hand, this is going to grow statically. It's going to, whenever something like a function call happens, we get a new stack frame, and that's going to include space for all the variables that are at any point created within this scope of this function, let's say. So if you create a function, and throughout the function you create int a, b, c, and d, it's going to actually reserve the memory for those right at the start of the function. It's going to compute how much space all those variables need. This is why older implementations of C actually required you to initialize all variables at the top of the function, because it would just check that, get those first few, um, so it could grow the stack from there. Um, in the modern day, though, the compiler will actually go look through the function and find all stack initializations, and will combine those all together to get a full size of the stack, so it can increase that and we'll be good to go. So that's that. Oh, the other one, of course, is args, environment variables, and all that. That's actually stored usually above the stack, and that is from the process table. But we'll have plenty of time to talk about the process table at a later date. For right now, let's get into this kind of example program here. So we have global memory, of course. This is initialized before we call main, stored in section B, initialized data. And at the same time, we also have our global Y, this is uninitialized global memory. This is going to be in the BSS section C. Worth noting, though, that all these bytes are going to be zeroed out as well. It's just going to 0 byte everything in the uninitialized global memory. We're saving this for later, but it's worth noting that this struct I've created here is 1 integer and 4 characters, meaning that it is 64 bytes in total. Some implementations of C will do weird things, like have metadata that makes it actually a little bit bigger. Pretty sure this version we're good. I've tested this version, so it does the job. This is actually just 64 bytes, which is what we want it to be. But beware of that as a possibility that can happen. And that'll usually be the case in other programming languages too, as most other programming languages will have their sort of structure object as being having some metadata, but this doesn't, which is nice. We have this helper function here. I wanted to note that we'll be using it later just to print our integer lists. I did want to note that we take the list as a pointer. This is because arrays in C and pointers are the same thing, and we'll get to that in a little bit. But the important idea to take from that is that whenever we have like this bracket notation here, this is the absolute same as doing pointer arithmetic to get to this. There is no real distinction under the hood between a pointer and an array. We'll look at these two in a little bit. But now we get to main. So this is where we actually get into it. First of all, we have our local string. It's a local variable. It's going to live on the stack. This literal itself might actually be in the text, but this actual char star is going to be in the stack. I've seen people try to trick people. Sometimes people ask, like, okay, is there different memory for main? No, main is just another function. It's going to also just live in the stack. And it's worth noting that this will not live outside of the function. So in main, that makes sense, because main is usually when main ends, the program ends. But if we have another function and we expect to return this char star or something, char star, it might work because usually that's pointing to a literal. But for like int star, if you had an int star that was a pointer to an integer that you were returning from a function to another function, if that's from the stack, it's not going to work because that integer is going to go away. The stack is going to clean itself up when it leaves a function. It's going to roll the stack pointer back when it leaves the function. And that's the thing about the stack, is it's not going to survive indefinitely. So primitive types can be moved around with the stack memory without much worry. This is because we know the size of them. We can pass by value this stuff. We could do the same with structs too, but there can be weird different things that can kind of mess with that. But generally, if your function's asking to return an integer, you can just return the integer. That can be from the stack because it's going to pass by value that. So let's take a look at so yeah, we can let's look at some initialization from the stack. In this case, we'll create some arrays. So we create our first array here, int stack int list1 size 8. This list, we didn't specify what the actual values are. We just have a list that is size 8. That's made of integers. So it's going to be 8 integers. And it's going to be from garbage data. So if I'm correct, it could be anything. Though sometimes, depending on your implementation, again, stack will be zeroed out. I don't think it is in this case, but we can see when we print it, I guess. We have stack list 2 here. In this case, we didn't specify an exact size because we actually treated this as an array literal. So we have 10, 20, 35, 100. And this last one is mostly going to be used later, but this is an unsigned int list. And you see we have 4 integers in here, which is, those 4 integers are then 4 bytes each, so 16 bytes total. And this will be used at the end of this little program. So when we want to do a print call, we can actually pass this local pointer in as an argument. I said before that got to be careful when using the stack and passing things around to other functions. But if you're passing it into a function from the outside, that's okay because this function is being called from inside of this function. So that when we make the stack bigger, we increase it by however many sizes and bytes when we start main. And we don't decrease it that many bytes until we end main, all the way down there. So if we're calling something like this, we can pass in that pointer to this print list here. Because it still exists in the memory. It still exists in the stack at this point. When we start print list, we're actually going to increase the stack. So we'll make it bigger. And then when print list done, it's going to get smaller again. But still, all of this data is safe and sound until the time that main ends. So we pass that in. And remember, we said this is an int stack int list 1 array. So this is an int array. That is the type of this. And up here, we have named this an int pointer. Because again, lists and pointers are the same thing. So the way this works is we can actually go through this like an array still. We're still using this bracket notation, which is kind of nice because we don't have to worry about doing pointer arithmetic as expressly. We already have a notation for it. Where were we? There we are. An example of one thing that won't work well. We have this bad string function. So this, if you try to compile it, it'll actually yell at you. In this case, we create a char array woot. We try to put woot woot in there with string copy, and then we try to return it. This will not work. Why? Because we increase the size of the stack to be able to hold this char array, and then we decrease it when the function ends. We clean up the function, and because that happens, when we return this pointer, again, this looks like an array, it's a pointer too, it's pointing to something that is ahead of the stack. It's pointing to garbage data. So C will not like that. Sometimes it'll work actually. If you ignore the warnings, because there's not going to be some program rummaging around, hopefully, and changing that data. But it's not safe. It is unspecified behavior. We might end up with something that breaks that way, or crashes, or whatever. Instead, though, if we want to be able to fix that, we can use this good string function. This does the same thing, except we're using stirred up. Stirred up is a good function. It is basically going to create a duplicate of the string using malloc internally. So this gets mallocked and will live on the heap. And that's the big difference between the stack and the heap, is that the heap, it doesn't get cleaned up until you tell it to get cleaned up. The stack will, on the other hand, clean itself up. So there's that. In this case, we have our we're showing how to use malloc here. So malloc returns a pointer. We need to say that the size we want is the number of whatever element we're using times the size of that element. This is the safest way to go about doing that. This is returning dynamic memory. So this is in the heap. This persists until we actually free it. We say free malloc int list. And this is going to include malloc, calloc, which zeros everything, or it doesn't even necessarily zero. You can set it to anything, but zeros everything. Actually, I think it just does zero everything. Never mind. Yeah, it zeros everything. Malloc can be anything. You'll have to zero it yourself or not worry about it right over it. And realloc is just usually what's happening there under the surface is something along the lines of just freeing it and mallocing it again, something along those lines. It can be a little more efficient than that at times, but not always. So we can also see something like this, where we try to print this list. We're saying that we have this malloc int list we had that we malloc before, and we already freed it. So we can try to put this in, and sometimes it'll work. This is a free after use, basically. And it's non-deterministic, so this is a really nasty bug to have. The best way to handle it, I suggest, anytime you free a pointer, go ahead and set it to null. Because this pointer variable is still here. It's just the data that it's pointing to isn't there. So you can take that and just say equals null. And when that happens, you'll get a seg fault exactly when it's used again. It's generally good practice to do this after every free. It's not particularly inefficient, and it'll stop you from getting weird bugs that are hard to track down. So we have an example of calloc. So calloc, we have to actually specify not just the size of the bytes, because in this case it just gives us the memory and doesn't worry about it any more than that. In this case, because it's zeroing everything out and it wants to know what the size of each thing is, we have to say how many elements and the size as separate arguments instead of a multiplication that ends in one argument. So if we print that, that'll give us all zeros. And with that malloc knowledge, we can do that. Again, stirred up is using malloc inside of it. So if you're ever, make sure that anything you stirred up, you free. That's important, because I did that there. And the reason for this is you'll get something called a memory leak. If you're doing like a quick one-off program that runs, spits out some data, and ends, it's not a big deal. It's not good practice, but it's not a big deal because it'll all get freed up at the end of the program. The whole memory space is no longer in use. But this could be bad for a long-running program, which in systems programming, we have a lot of these programs that are actually meant to constantly run for their whole life cycle, basically, to just continually go. And this freeing problem will slowly eat up your memory and cause more of a performance hit as it goes. And that's why it's an insidious, dangerous problem you can have in your software. Again, not a huge deal if your program just runs real quick and ends, but big problem in the long run. So here we create x equals 25, and the reason for that is I wanted to show that we can create a pointer to a variable in the stack pretty easily. Variable anywhere, really. Use our ampersand to ask for a pointer. And we can then dereference that pointer to get that value. So that'll give us 25. The thing is, again, pointers are arrays. So we can also, if we want to dereference it with the star XP, we can do that. This is the same thing. XP bracket 0. So that's just something to think about, is this idea, again, that this memory is not a particular type. These types that we assign to it are abstractions for our benefit. The memory itself, we can say it's a pointer, it's an array, whatever. We could also modify that pointer, of course. We can do that. We could also do it this way, where we say xp0 again equals 13. And this will give us our new values. And this changes the values of x. So this that we made here, we haven't actually touched this variable this whole time. And yet, when we finish, its value is still going to be 13, because we've been touching its memory location, just not the variable itself. So again, this to finally wrap this up, and I've been harping on this for a while, so you can tell that it's an important idea, not just in systems programming, but in computer science in general, that these types we have don't exist. They're abstractions. They don't exist in memory, and they're not treated in any sort of special way, unless they are. You can totally have a programming language where you embed your typing inside memory, and they do that. But in C, certainly, C is so low level that we don't have these types embedded into memory. It's just all bytes. It's all binary data. So for example here, we have the stack int list array. We saw that back here. It's this one. We can treat it as a char star instead. So we take this list, we convert it to a char star, and now it's a byte list instead of an int list. So we go through that. It's going to be 16, of course, because there's 16 bytes in this. And we'll see that it'll print out each of these bytes. So it should print out 0, 0, 48, 57, 4 zeros, 3 zeros, 25, and then 4 65s. So that's great. We can treat an integer as a bunch of characters if we want to. But it doesn't just go that way, where we're going from a primitive type to a smaller primitive type. We can also do this with non-primitive types, with structs. So in this case, I have this item struct. Again, this is going to be, has an integer and then 4 characters. 64 bytes total. Of course, our integer list over there is going to be 128 8 bits. I was doing bytes is not correct. This is, here we go. So we have 4 bytes for the integer and 1 byte for each of these. I was thinking in bits. So in fact, we're just going to have 8 bytes here. Good stuff. So anyways, what we can tell from this then is that an item is going to take up 2 integers worth of space, which makes sense because we said we have an integer and then we have 4 characters, which are each a byte. So again, we have 2 now. We've converted this list again into being a struct item star. And we can go through those 2 items and gather each of the different data values from them. And in fact, let's run our program. See, it's updated through WinSAP. Here, make run. So we have all of our lists. You see stack list 1 here. This was our one that we don't have initialized, so it's not going to be all zeros. It's just going to be garbage data. Stack list 2, we initialize that, so it's going to be its own data. We can see that malloced int list is zeros right now. It doesn't have to be. It often won't be. In this case, we lucked out. But calloc is always going to be zeros. We got our correct woot sent over. That wasn't that was gathered using malloc. We have our x values we talked about, and we see how it actually ends with 13, even though we didn't touch it that whole time. Finally, we can see our int array as other types. So in this case, we have our stack list. We have all in bytes. I printed the decimal versions. And we have our array as items here. So we have 1, 2, 3, 4, 5 as our first integer, and 25 as our first integer for the other one. And zeros for these are just nulls that got inserted, so you can't really see them. But for this one, it was all 65, so capital A. And to wrap everything up here, let's look again at this one more time, at this idea that classes in memory or structs in memory or any of these types, any of these abstractions that we have aren't really in the memory. Here we have the memory itself, main memory. We have all these different bytes all lined up. We can think of the byte as our atomic unit here. And we have an integer type. This integer is just a mask. It's just sitting over this part of memory. And it's saying that all of these bytes are included in the integer. So the integer itself is just a concatenation of these bytes all together. Same with the char, except the char is 1 byte, so it's a concatenation of 1 byte. Trivial concatenation, I guess we'll call it. And then an item type, a struct here, is just the composition of these other types we have. So for example, we have A, which is an integer, and we have B through E, which are characters, and that forms this type. So these objects are more masks over memory than anything else. It's an abstraction is what it is. And that's something that I remember my 180 professor many years ago actually said. One of the first lessons he taught us was that programming at its fundamental level is all about abstractions. And that's what I hope you got from this little primer video in C memory. We're going to do another one on C++ memory and how that can be a little different at times. But otherwise, that's it. Peace.